I can. Here it is. It will disappear quite soon. First time you see my face, because previously you saw a face mask on my face. All right, so today we start our lectures online. So the rules are the following. I advise you to keep your mic and your camera off. But in case you have questions, don't raise your hand or do complicated things. Just turn on the mic and stop me, as in class. And we'll keep going that way, okay? So please stop me for every question. So as you remember, for me, it's quite hard to remember names. So maybe it's better also if you want to ask a question to turn on the video. This way I will recognize you, okay? Okay, so let's start. I will turn off the camera now to have a more stable connection and share the screen. Okay, and now we go on the camera, and here we are. So ready for to continue with our introduction to statistical mechanics. So essentially, what we have seen last time is that the postulate on which the entire building of statistical mechanics is based is the equal a priori probability. Postulate. And the postulate says essentially the following. It says that if I have a system that has a certain phase space, for example, let's have in mind a gas. And so in this case, the phase spaces are the positions and the momenta of all my particles, and I varies between 1 and n is the total number of particles in my system. And if this system is described by a certain Hamiltonian H, which is written up here, then what we want is that the probability density to observe a system in the neighborhood of two momenta Qi and Pi is equal to a constant if the energy of the system is between E and E plus delta and is equal to 0 otherwise. In particular, we can ask ourselves, what should be this constant? Well, we know that the probability distribution should be normalized to 1, and therefore, obviously, the constant is equal to 1 over the volume in phase space of the thick, I mean, kind of lasagna, the thick surface in phase space identified by this condition here, by this condition. So the volume in phase space is nothing but 1 over integral dq I dpi E smaller than, actually, let's forget dq dp. Okay, let me write things and then I'll explain a notation that will simplify our life in the future. Product over I dqi dpi. So instead of writing this product in the future, I will just write dq, dq dp. Okay, so when I write dq dp, we understand that it's the product over all i's of the three-dimensional volume elements dqi and dpi. All right, so it's just a shortcut notation. So in particular, it's convenient to give a name to this, and let's call it 1 over gamma of E. So gamma of E is the volume in phase space of the thick lasagna. You remember the figure that I've drawn last time, where I had an hypersurface of constant energy, and the condition of having essentially of having the energy in between E and E plus delta, where delta is some kind of resolution of my measurement apparatus, makes this surface area, this surface thick, gives to this surface a thickness, and this is the volume of this thick surface. All right, so now we are essentially ready.
Professor?
Yes.
Sorry, I don't get the definition of volume in phase space. So
Well,
is it gamma E or the constant?
No. Gamma, sorry. So gamma of E is equal to integral dq dp. Okay?
Oh, so gamma is the volume in phase space.
Yeah, that's what I said. Is the volume in phase space.
Oh, the constant is the density.
Well, the constant is the inverse of the volume, because if I integrate over the entire volume, right? So this constant has to be equal to 1 over gamma, because the integral dq dp of rho has to be equal to 1, right?
Oh.
You see? It's a probability density.
Yes.
And therefore, you have to set the constant equal to the inverse of the volume in phase space, right?
Yes.
Good. All right, so we are now ready to introduce the entropy, to introduce the basic idea that that makes the connection between thermodynamics and microscopic dynamics, between the macroscopic world and the microscopic world, concrete. And this basic idea is the statement that the entropy S is equal to K Boltzmann times the log of gamma of E. So you're given a system that has that is isolated. It has some macroscopic conditions, given energy up to an uncertainty delta, given volume and given number of particles. Now the statement, what Boltzmann, Mr. Boltzmann, Ludwig, what Boltzmann said is that the entropy, the thermodynamic entropy, is equal to K Boltzmann times the log of the phase space volume gamma phi. Okay? This is Boltzmann's main idea. And if you think for a second, this idea comes exactly from that little exercise we have done in thermodynamics, you remember, for the for a system, for a gas in which the entropy was k Boltzmann times the log of the number of ways of putting n particles into small cells without counting permutations. All right, so whenever I write something of this type, what is the first thing I should ask? I mean, I'm pretending this formula to give me the entropy, right? So what is the first most important thing the entropy should be in order to check that this formula has some hope to be correct? This is a question to you guys.
Of course, we know that the entropy.
Can you speak in the microphone because I cannot hear you?
Hello, can you hear me?
Yeah, kind of, well, weak, but I can. Please.
Yeah, I said that the entropy, we know that it should be an extensive property as we've proved in class.
Exactly. Very important statement. The entropy S is an extensive variable. And therefore, the question we have, the first question we have is this definition corresponding to an extensive variable or not? So now, I mean, there are various ways to see that this is extensive. One way could be to just say, well, look, guys, gamma phi is exponential, is a quantity that is exponentially large in the number of particles, is something to power n. And therefore, if you put it in the log, the n will go out, and it's going to be proportional to n overall, right? So gamma phi is of order something a to the n. And therefore, this implies that S is proportional to n. Now, if you think for a second, I'm sure that you can easily convince yourself that this volume in phase space is exponential in the number of particles, and therefore this simple argument is correct. However, this simple argument is not entirely satisfactory because, well, we would like also to see more concretely how to derive thermodynamics from this, and what are from this formula, and whether this formula gives us correctly the conditions, for example, of thermal equilibrium between two subsystems that are connected together. You remember, for example, that when we took two subsystems like this, what we said is that if you have these two subsystems with a given energy E1, a volume V1, and a number of particles N1, and E2, N2, and V2, we said that the condition of thermal equilibrium is that ds1, dE1 is equal to ds2, dE2, which means that the two temperatures essentially are identical, T1 equal to T2. Well, we can ask ourselves, given this definition of entropy, will this condition for equilibrium follow? I mean, is the entropy behaving as an entropy? Okay, so let's see that this works. exactly by using this formula to describe the situation I just described here. So let me just pick this and copy it to the next page. Copy to describe the situation in which I have these two subsystems that are connected together. And now I want to show that the entropy is extensive, and at the same time show that the conditions of equilibrium between these two subsystems are exactly the ones I wrote down before that come up, that were derived before in this course using just thermodynamics. All right, so we have these two subsystems. The first one has some phase space described by a set of variables Q1i, Qpi, right? For the total number of particles N1 that are sitting in this subsystem that occupy the volume V1 with a total energy E1. Sono stato. Okay. And the second system is Q2, P2, with a number of particles N2, volume V2, energy E2. Okay? Now, the total energy, which is again described by this fancy H, is the sum of H Q1 P1 plus H Q2 P2. Of course, when I write Q1, what I mean is all the variables in the first gas, and Q2, all the variables in the second gas. Now, when you see this formula, you could start complaining, because in principle, if I have the energy, which is the sum of these two terms, I should add an extra term, plus, that describes the interaction between all particles that are sitting in subsystem 1 with all particles that are sitting in subsystem 2. However, if the interactions are not too long ranged, if you think for a second, all these interactions live on a surface, that is separating the two subsystems. And therefore, since this one is scaling like a volume, this one is scaling like a volume, but this interaction term would be scaling like a surface. In the thermodynamic limit, where these volumes are very large, it can be neglected. Okay, so that's the logic of not even writing it. Okay, so now let's fix the energy and compute the entropy. Well,
sorry.
Yes.
Can you repeat the last argument why you neglect the interaction?
Well, so this one is scaling like a volume, right? It's proportional to a volume. This one is proportional to a volume. But this term here would be proportional to surface A, that is the area that is separating these two subsystems. Here I drew everything in 2 dimensions. In order to show you what is the area, I would have to draw it in 3 dimensions, like this, and the area would be this. But now you realize that when I send my system size to infinity, right? The surface term is much, much smaller than the two others that are scaling like volumes. Subleading, this is the right terminology. And therefore, in the thermodynamic limit where V1 and V2 are very, very large, it can be neglected, okay? So that's why I'm not writing it. I'm assuming that the energy is the sum of these two terms, which makes a lot of sense because the energy should be additive. And is additive unless you have long-range interactions, which are not the case. I mean, I will never be talking about systems with real long-range interactions in this course, because thermodynamics and statistical systems with long-range interactions is complicated and is beyond the scope of what I want to tell you. All right, so the energy is additive, which means, but now what I want to say now is that my total system is thermally isolated. The total number of particles is fixed and the total volume. And in particular, if my system is thermally isolated, what it means is that my energy, E, is fixed. But what is fixed are not the individual energies, E1 and E2, but rather there's some E1 plus E2. Okay? And in particular, if I want to compute the entropy of the entire system, the entropy is defined by the fact that E1 plus E2 should be comprised between a certain energy E and E plus 2 delta. You will understand the meaning of this factor of 2. I mean, it comes essentially from having two subsystems, but it's essentially the resolution of my apparatus again. All right, so let's now focus on the two subsystems, 1 and 2. And in particular, select two values, E1 and E2, two specific values for which this condition is satisfied. So select E1 and E2, two specific values for which this condition is satisfied. Well, let's call it condition.
Excuse me?
Yeah, just a second. Just one second. For which condition 1 is satisfied. Yes. Yes, please.
Yeah, can you explain like briefly why do we have E plus delta plus 2 delta?
Well, so the 2 delta comes because I will assume that E1 is determined up to a delta. E2 is determined also up to a certain delta. The 2 delta are identical. And therefore, their sum is determined up to a 2 delta. Okay? In other words, if your apparatus with which you measure E1 has an accuracy delta, and the other one has an accuracy delta, the accuracy with which you can measure E1 plus E2 is twice that, right? I mean, at most, E1 plus E2 can fluctuate by 2 delta. You will understand it well if I write another few lines, okay? All right, so let me consider, as I was saying, E1 and E2, E tilde 1 and E tilde 2, okay? For which this condition is satisfied. So for which E tilde 1 plus E tilde 2 is in between E and D plus 2 delta. Now, what is the volume in phase space for corresponding to E tilde 1? Well, this volume is going to be given by the integral E tilde 1 smaller than H1 smaller than E tilde 1 plus delta dq1 dp1. Now, I can do the same thing for E2, E tilde 2. The volume in phase space corresponding to this specific value E tilde 2 is going to be equal to the integral E tilde 2 smaller than H2 smaller than E tilde 2 plus delta dq2 dp2. And therefore, considering the fact that the entire phase space is given by essentially the product of all variables.
Sorry, Professor.
Yes.
What's the difference between the E1 and the H1?
Well, E1 is a value of energy. H1 is a function of phase space variables. So what I'm saying is that let's choose two numbers. So H is a function of Q1 and Q2. It's like an Hamiltonian. It is an Hamiltonian. E tilde 1 and E tilde 2 are just some values of the energy. I'm saying, I know that the energy is the sum of the energy of the two subsystems. So let's choose two specific values, E tilde 1 and E tilde 2, for which their sum lies between E and E plus 2 delta. Okay? Now I want to compute for these two values. If I choose these two specific values, what would be the corresponding volume in phase space that correspond to all particles in the first system having an energy around E tilde 1, and all particles in the second subsystem having an energy around E tilde 2. Okay, you see what I mean? Yes or no? Yes or no, or perhaps, or sometimes. Yes, can I go on?
Yes.
Okay, good. All right, so now I'm asking myself the following question. Given these two specific values, E tilde 1 and E tilde 2, what is the phase space volume that corresponds to having all the particles in 1 having around this energy E tilde 1 and all the particles in 2 having around the energy E tilde 2? And the answer is that the phase space volume gamma will be equal to the product of the phase space volumes gamma tilde 1 times gamma E tilde 2. Okay?
Sorry, Professor?
Yes?
Why it is the product?
Sorry?
Of the two? Why it is the product of the two gamma?
Why it is the product?
Yes.
Well, so let me put it this way. Suppose that your phase space is the phase space of particles 1 is one-dimensional, right?
Mhm.
So in which case a phase space volume would be just the length of an interval, right?
Yes.
If the space was one-dimensional, just one variable, not even two, one, it would be just the length of a line. Then for system 2, it would also be the length of a line, right?
Mm.
And now I'm asking myself, what is the the total phase space is the product, the direct product of these two guys, right? And now I'm asking myself, what is the phase space volume that of the entire system that corresponds to having these two conditions satisfied? Well, it's going to be the product of this length times this length, right?
Yes.
In other words, the area of this. So this is the idea. Right?
Okay. Thank you.
All right. Now, however, you should keep in mind that this is true only if I select two specific values of E tilde 1 and E tilde 2. But now, what I have to fix is not the values, the specific energies of the first subsystem and the second subsystem. What I have to fix is the total energy, because the total system is closed, but the energy between 1 and 2 can be exchanged, okay? And in other words, I can ask myself, what is now the phase space volume of the system, of the entire system, 1 plus 2, or 1 times 2? Total volume, what is gamma of E for the entire system? If I let E1 and E2 fluctuate, but keep E1 plus E2, of course, between E and E plus 2 delta. Now, the answer is the following. Take the interval between 0 and E and divide it into equally spaced subintervals. With a spacing that is set by the resolution of your instrument delta, and the corresponding energies, call them EI, in such a way that essentially E1, I call it EI, and E2, I call it E minus EI. You see that if I write things this way, the condition that E1 plus E2 is equal to E is satisfied automatically, right? Now, for each EI, I can now compute, or for each one of these two values, EI and E minus EI, I can now compute the surface, the phase space volume corresponding to these two values, gamma, which is going to be gamma 1 EI, gamma 2 E minus EI. And now the total phase space volume, if I now keep only the sum fixed in this interval E plus 2 delta, but not the individual values of the two energies, is going to be given by the sum for I equal to 1 E over delta. E over delta is just the number of intervals, the number of crosses up here. Just count them. Of gamma EI, gamma E minus EI. Okay? So this is my total phase space volume. Now I take this and I have to use it to compute the entropy. So I take what Boltzmann tells me, and I have that the total entropy is equal to K Boltzmann times the log of sum over I gamma EI, gamma 1 EI, gamma 2 E minus EI. Okay? All right.
Professor,
Yes.
the sum in the box you make is also gamma 1 and gamma 2.
Yeah, absolutely. You're right. Gamma 1 and gamma 2.
Can I ask why you make it like that, the formula?
Why I make it discrete? Well, I could make it continuous, right?
What is gamma 1 and gamma 2 and yeah?
What is gamma 1 and gamma 2?
Are you
defined here? Okay.
Are you summing
gamma
all
1.
over the I? Why
I'm
are
summing
you?
over the I.
Yeah, I mean all
Well,
the I is all the points here, right?
Yes, absolutely. I'm essentially assuming that I have a finite resolution to determine the energy, and therefore I'm summing over all intervals within that resolution between 0 and E.
Okay.
Okay,
So,
that's the logic.
actually, I still have the question for the previous one where you calculate gamma is equal to gamma E1 times gamma E2. I mean, gamma E1
Yes.
and gamma E2 is like both of them are volume in phase space, right?
Yes.
And then why you can suppose them as a line and then you can count them as
Well, look, let me make it. Suppose that you want to compute a volume in phase space like this one, right?
Yes.
The volume in phase space in which you fix the value of one of the energy in one and you fix the value of the energy in two. So this is equal to the integral dq1 dp1 dq2 dp2. Then I'm fixing the energy in one, so therefore E1 smaller than H1 smaller than E1 plus delta. And then I'm fixing the energy in two. E2 smaller than H2 smaller than E2 plus delta, right? This is my total volume gamma under those conditions. And now you see that this integral factorizes into two integrals, dq1, dp1, dq2, dp2, right? Where the first one is 41 and the second one is 42. Right? So what I wrote here is nothing but this factorization.
I see.
And I tried to explain it using geometry, but it's just a factorization of two integrals.
Okay.
All right. So, all right. So this is the entropy, my total entropy. Now, what do I do with this? Well, what I do is the following. Suppose now that we have E bar 1 and E bar 2, right? For which this product, gamma 1, E bar 1, and gamma 2, E bar 2, well, of course, these two guys, their sum is between E and E plus 2 delta. So E bar 1 plus E bar 2 is between E and E plus 2 delta. And we have that gamma 1, E bar 1, gamma 2, E bar 2 is the largest term in this product. Okay? It's the largest term in the product. Now, what do I have? Let's look here. I have that my, okay, let me copy this and take it to the next page. Copy. I have the following. I have that my gamma, certainly my gamma of E is larger than gamma 1, E bar 1, and gamma 2, E bar 2, right? Because this is just one of the terms in this sum. All the terms are positive, and therefore this guy is certainly larger, at most equal than this product. But it's also smaller than E over delta times gamma 1 E bar 1 times gamma 2 E bar 2. Why? Because this is what would happen if all the terms in this sum, which in total are equal to, are in number E over delta, would be equal to the biggest, to the largest, okay? And therefore you must have this inequality.
Sorry, can you
Yes.
go back to the previous page? I missed the last point.
What?
Oh, so gamma 1, E1 is the largest.
Yeah. So I'm choosing E bar 1 and E bar 2 in this sum in such a way that gamma 1 E bar 1 and gamma 2 E bar 2 is the largest.
So that's
The
why you
large,
get this inequality.
absolutely. That's why I get this inequality. I choose them on purpose. All right. And now I take the log of this. So I have that log of gamma 1 E bar 1, gamma 2 E bar 2 is smaller or equal than log of gamma, which is smaller or equal than the log of gamma 1 E bar 1, gamma 2 E bar 2, plus the log of E over delta. Now you see something quite interesting. Log of gamma, so, okay. So this tells me that log of gamma is in between log of gamma 1 E bar 1 plus log of gamma 2 E bar 2 plus log of E over delta smaller than equal than log of gamma 1 E bar 1 plus log of gamma 2 E bar 2. In other words, we get that the total entropy is additive, because this is S1 plus S2, and this is S1 plus S2, up to corrections that scale like log of the number of particles or the volume or whatever, because the total energy is extensive. So therefore, this term log of E over delta will scale like log of V or log of N.
Sorry, sir.
Yes?
So we know that the energy is a function of the number of particles.
Yes.
Yeah.
Yes.
And what we've tried to do is that for these subsystems, we try to consider them as one entity within the phase space. We
Yes.
calculated the volume within
Yes.
the phase space.
Yes.
However, we also know that because in what we are trying to do, we wanted to show that the entropy is extensive, that is additive. But
Yes.
This from thermodynamics, it's clear to us that there is we don't have some other corrections. The n usually is always zero. Sorry, not zero.
Which N is zero?
I mean the correction. There is no other correction. It's a perfect.
Of course, there is no correction, but thermodynamics, as I told you many times, in order to get thermodynamics from microscopic theories, you have to go to the thermodynamic limit, right?
So,
what is the thermodynamic limit? The thermodynamic limit is the limit in which the volume goes to infinity, the number of particles goes to infinity, and their ratio is constant. Okay? You see that if I take the volumes to be very, very large, again, as before, this will scale like volume. This is going to scale like volume because it's additive. You see, is between two quantities that scale that are additive, so it's going to be additive, up to corrections that are subleading because scale like log of n. And therefore, in practice, in the thermodynamic limit,
n will go to infinity.
the thermodynamic limit, what I have is that S is equal to S1 plus S2. Because these corrections can be neglected.
Yeah.
Okay.
N go to infinity, so the log of n is 0.
Well, no. Log of n is large if n goes to infinity. Is large, but log of n, if you take the ratio of the correction to the entropy that scales like n, log of n over n goes, as n goes to infinity, to 0.
Oh, I see.
In other words, this term here is much more important than this in the thermodynamic limit. It's much, much larger. It's like 10 to the 6 plus 1. It's still 10 to the 6, right?
Yeah,
You see what I mean?
Mm.
It's much, much larger. And therefore, this other term can be neglected. All right. In the thermodynamic limit, therefore, I have this identity. And now I can ask myself the following question. Okay, I discovered that in practice, in the thermodynamic limit, the entropy of E is equal to the entropy S1 at E bar 1 plus S2 at E bar 2. And what were E1 and E2? They were the terms for which the volume gamma 1, E1, gamma 2, E bar 2 is the largest. Right? This is what identified those two values of the energy. All right, so let us, in order to figure out what this means, let us write down the condition for this to be the largest. I want the variation of this, I want this to be a maximum, and therefore the variation should be equal to 0. Gamma 2 E2, and this is equal to delta gamma 1 gamma 2 plus gamma 1 delta gamma 2. So this should be equal to 0. This implies that delta gamma 1 over gamma 1 should be equal to minus delta gamma 2 over gamma 2. Or, in other words, that d gamma 1 over dE1 1 over gamma 1 times delta E1 should be equal to minus d gamma 2 dE2 over 1 over gamma 2 delta E2. But now the point is that E1 plus E2 is fixed, is equal to E, right? So let's keep this in mind. Since E1 plus E2 is fixed and is equal to E, that is given, then delta E1 is equal to minus delta E2. And then I can change variables in this integration. And I can easily write down this as delta gamma 1 over delta E1 1 over gamma 1 delta E1 is equal to delta gamma 2 dE2 1 over gamma 2 delta E1, because delta E1 is equal to minus delta E2.
Professor,
Yes?
sorry for asking about notation. So you said delta gamma 1 over delta E1, or is it partial derivative or?
Yeah, it's of course partial derivative. It's a partial derivative of gamma 1 with respect to E1 and partial derivative of gamma 2 with respect to E2. It's not a delta, it's actually is d gamma 1 dE1, d gamma 2 dE2. Thank you. Okay, so you see that this identity should be satisfied. But what is this identity? This identity is the derivative with respect to E1 of the log of gamma 1 should be equal to the derivative with respect to E2 of the log of gamma 2. In other words, what I want is that the derivative of the entropy S1 with respect to E1 is equal to the derivative of S2 with respect to E2. But we know that, first of all, this is in thermodynamics, this condition, we already met this condition, and this condition has the meaning that the two temperatures, T1 and T2 of the two subsystems have to be identical, right?
Sorry, Professor.
Yes.
Can you explain the last line, logarithm of gamma 1?
So the 1 over x derivative, or let me write it like this, 1 over y dy dx is equal to d dx log of y. You agree with me? You agree?
Why d over dx? Why not 1 over dx? Because
I don't understand. So let's do this derivative together. D dx log of y is equal to d log of y dy dy dx because of the chain rule, right?
yes,
Of derivatives. Now d log of y dy is 1 over y, right?
yes.
dy dx. So you see, it works.
Okay.
Now substitute to y gamma 1 to x E1, and you see that it works.
Okay, thank you.
No problem. All right, so we see that we get essentially the same condition that we got in thermodynamics to represent the thermal equilibrium between the two subsystems as essentially the well, as a condition of the temperature. The derivative of the entropy with respect to the energy is the inverse temperature. So, and therefore, if I want the two subsystems to be in thermal equilibrium, I have to have that 1 over T1 is equal to 1 over T2. Now, the Boltzmann definition of, so the bottom line is, the Boltzmann definition of the entropy makes a lot of sense because not only the entropy I just defined is extensive, but the condition of equilibrium that I find for two subsystems is exactly the same as the one I find in thermodynamics. Okay? And therefore, everything is perfect and beautiful. Now, in practice, statistical mechanics comes or starts or is born whenever I give you some rules to rederive thermodynamics from something that is microscopic. So now, in this setting, which is called the microcanonical ensemble, I never said this word, but I'm sure that you know, microcanonical. Now, in this setting, what I have is that the total energy is fixed, the total number of particles is fixed, total volume is fixed. If I have a gas, if I have a system of spins, I'm just fixing the total energy and total number of spins. So what I said is that in order to use statistical mechanics in this setting, the only thing I should do is compute this phase space volume gamma phi. Once I know this phase space volume, I can just compute the entropy as equal to K Boltzmann log of gamma phi. And once I know the entropy, I can rederive all thermodynamics because I can essentially take ds dE at constant volume and compute the inverse temperature. I can compute the pressure from T, ds dV, etc. Well, and then I have ds equal to 1 over T dE plus P over T dV, and I'm essentially done. I can start playing with thermodynamics. Okay? So you see the connection works through a quantity, which is gamma phi. So you have to keep in mind, whenever you want to use the microcanonical ensemble, that what you have to compute is this phase space volume, or more in general, because the phase space volume is something that you compute in for a gas, for a system that has continuous dynamical variables. More in general, you want to compute the number of configurations of your system that correspond to a total energy fixed. Okay? We will see what this means later on when we will be solving in the microcanonical setting the Ising type models. Okay, so models with Ising variables that are essentially equal to plus or minus 1. They're not continuous variables. All right, so now let's move on. Before doing a small exercise with you, I would like to tell you that in statistical mechanics, there are various definitions of the entropy in the microcanonical ensemble, and they are all equivalent in the thermodynamic limit. Okay, this is very important. All the definitions of entropy in the microcanonical ensemble are equivalent in the thermodynamic limit. What does it mean? It means that the difference between the various definitions are by a factor that scales at most with log of n. So it's essentially irrelevant in the thermodynamic limit. It's subleading with respect to the extensive part. That is always the same. All right, so let me write the statement. In the thermodynamic limit, K Boltzmann log of gamma, which is what I wrote down before, is equal to K Boltzmann log of sigma, which is essentially equal to K Boltzmann log of omega. And all of them are the entropy. Now, gamma, we know what it is the volume of a slice of thickness delta in phase space. Sigma is the volume of phase space corresponding to all energies being smaller than E, dq, dp. So instead of taking a volume of a slice, I take the volume of all, I take the entire phase space volume that is closed by the hypersurface as constant energy, and that contains the point, the zero energy point. Okay? So, in other words, if your phase space volume, if your phase space was a sphere, so like in, I hope this drawing can, well, make some sense. So if your phase space was a sphere, then gamma is the volume of a, well, it's not a great drawing, but it's decent. Gamma is the volume that is inside here, right? So this is gamma. Sigma is instead the entire volume of the sphere. And what I'm saying is that if you increase the number of dimensions of your system, which corresponds to increasing the number of particles, both these volumes scale exponentially with the number of dimensions and scale exponentially in exactly the same way. Therefore, when I take the log, I will get the same up to factors that are subleading and that are not important in the thermodynamic limit. Is that clear? So you should think that When I say thermodynamic limit, what it means is that I'm increasing the number of dimensions of my phase space. If I have one particle, my phase space is 6-dimensional. If I have n particles, my phase space is 6 times n dimensional. And now the volume of a shell of a sphere or of the entire sphere, if I increase the number of dimensions, will scale with the total number of dimensions in the same way. Okay?
Yeah.
Both of them will scale like omega.
Sorry, Professor.
Yes.
Yeah, so sigma is, we can think sigma is the density of states having an energy E. And if we think about it as a sphere that has constant energy, enclosed sphere with constant energy, and if we have like a dimension that is like 3n, then we can think about the q raised to power 3n, the p raised to power 3n, something like this.
Absolutely, absolutely, yes.
Oh.
Yes. Yeah, that's the main point. So, but sigma is not a density of states. Sigma is the number of states, total number of states with energy smaller than. So it's not a density of states. What is a density of states is omega. Why? Because omega is the following. Suppose that I take gamma. Gamma depends on delta, right? Because are all states within a microcanonical shell of thickness delta. So gamma, I can write it as delta times omega, if I make an expansion for small delta, where omega is nothing but d sigma dE. This is a density of states. So this is what you wanted.
Oh, I see.
Okay?
Yes.
All right. So,
sorry.
yes, yes.
I still don't get the point where you say both gamma and sigma scales to the exponential to the power of the number of dimension.
So let's work out an example and you will understand perfectly well what I'm talking about. Okay?
Okay.
Okay. So let's work out an example. Okay, the example is the following. Let's take an ideal gas. Right? For the ideal gas, the coordinates, we know what they are. The Hamiltonian is sum over I pi squared over 2n. This is the Hamiltonian of the ideal gas. Pure kinetic term, no interaction whatsoever. Okay, so now I want to compute the how is it called? The entropy. So this is K Boltzmann log of sigma, log of gamma, log of omega, whatever, but I have to compute a phase space volume. So let us compute sigma. Sigma of E is equal to the integral for all h smaller than E of dq dp. Now, there is something wrong in when I write kb log of sigma. And I define sigma this way. What is wrong? That this sigma is dimensionful, right? As dimensions of an action to a power 3n, because dq dp has dimension of an action, like h bar. And here I have 3n such terms. Because for each particle I have 3 terms of this type, and then I have everything to the power n. Therefore, if I want to put it in the log, this sigma, I have to make it dimensionless. And in order to make it dimensionless, I have to put here an arbitrary constant with the dimension of an action, 2 power 3n. I'm calling this constant h, not because I'm, it's not a, let's put it this way, it's not a random choice, but I'm calling this constant h because actually when you derive classical statistical mechanics from quantum statistical mechanics, and this is going to be the semi-classical limit, then this h is exactly the Planck constant, which has the dimensions of a q times a p, a length times a momentum. Okay, so you understand why I have to normalize it.
Why is the power of 3n not 6n? Because for q and p you have 3n, right?
No, look, here I have, so what this means is product over I from 1 to n dq I dp I. Each one of them is a 3-dimensional vector, right?
Yes.
Now, h as dimensions as the same, so the dimensions of h are dimensions of an action, therefore the dimensions of a q times a p, right?
Oh.
You agree?
Yeah.
Yes. Therefore, you see, let's count how many products of this type I have here. For each I have three products of Q and P, right? For each I. And then I have n of them. And therefore, I have a total of 3n of them.
Mm.
You see why I put an h to the power 3n?
Yes.
Good. All right, so, but we will understand the meaning of this h to the power 3n only when we will be doing quantum statistical mechanics. At the moment, it's an arbitrary constant sitting there. But you know from the uncertainty principle, actually, that in quantum mechanics, the scale of phase space uncertainty is actually h bar, right? Because of the Heisenberg uncertainty relations. So it should not be surprising that here I would be normalizing with something of that type.
Also, Professor?
Yes?
When you say when we have n particle, is the phase space 6n or 3n dimensional?
Well, the total dimension of phase space is 6n, right? I have 6 times n variables. But the total physical dimension of phase space is an action to the power 3n of a phase space volume, is an action to the power 3n. The physical dimension in terms of units, right?
Yeah.
Okay. It's not, one is the mathematical dimension of the phase space as a vector space or whatever you want. So the phase space is R to the power 6n, right? I have 6n real variables in my phase space. But these variables are not dimensionless variables because they are momenta and positions. One has dimensions of a length, the other has dimensions of a momentum, which is a mass times a velocity, right? And therefore, the total dimension is an action to the power 3n. physical dimension, not mathematical. I don't know if I hope I explained what I mean. Anyway, so now that we normalize this, the integral in dq, we can easily do it. It comes out to be v to the power n, h to the power 3n, and then I have the integral over dp. For all h smaller than e, which means that I want sum over I pi squared smaller or equal than 2m times e. This is my condition. But now this is what? This is the volume of a sphere in how many dimensions? This integral here defines the volume of a sphere in how many dimensions? How many? Someone knows? What?
3n
3n.
dimension. Yes.
3n, exact, correct. In 3n dimensions. Now, if you have a sphere in n dimensions, then the volume is, let's call the volume omega, and for radius r is equal to pi to the power n over 2 divided by gamma to the power n plus n over 2 plus 1 times r to the power n. This is the formula. Unfortunately, I don't have time to prove it to you, but well, you can find the derivation almost everywhere, including on the internet. So you're more than welcome to check it out there. So let's call this constant here Cn. Now, in our case, the radius,
sorry.
yes, yes.
The integral in the circle, p
Yes.
Okay, p squared less or equal to, I don't see that letter. Is it mu? Is it m?
M times e.
Okay.
M is the mass. You see, is the same letter is sitting here. Okay, so now if I use this formula, what I get is that this is equal to v to the power n divided by h to the power 3n times c to the power 3n times what? What is the radius? The radius is the square root of sum over I pi squared, right? So therefore, the radius of my sphere is square root of 2me to the power 3n. So this is the radius of my sphere. Now, what I would like you to notice here is that you see that the radius increases exponentially with the number of particles. If the number of particles increases, the radius, sorry, not the radius, the volume, sigma, increases exponentially. You see? Now, coming back to the previous question I was asked. You wanted to see why sigma and gamma are scaling in the same way. Well, gamma is is by definition sigma at E plus delta minus sigma at E, right? Because if I want to calculate the volume of a shell, I just take the volume of the biggest sphere and subtract the volume of the inner sphere, right? And I have the volume of the shell. Now, but now you see that this guy is going to scale like something to the power n. This is going to scale like something else to the power n. Something, well. And therefore the difference is still going to scale in the same way with the number of particles. Let's do the calculation later on. Maybe now you don't see it very well, and now I don't have much time. So, but this is essentially the logic. Yes.
I don't get the part where you say volume gamma increases exponentially.
Let me answer this question later on. Okay, let me move on for a second and get to the end of this calculation, and then you will hopefully well, actually, no, let us do it now. So this is the result, right? Now, let us compute, this is sigma. So let me take it here. Copy and paste. So let me now do the following. What is gamma? Gamma is sigma of E plus delta minus sigma of E. Right? You agree with this? Yes or no?
Yes.
Good. Okay, so let's now substitute. This is V to the n, H to the 3n, C to the 3n, and then I have square root of 2me plus delta to the power 3n minus square root of 2me to the power 3n. Now this is equal to V to the n over H to the 3n, C to the 3n, and I rewrite this as square root of 2m times e to the power 3n times, just a second, times the square root of 1 plus delta over e to the power 3n minus 1. You agree?
Yes.
Okay. So now let's assume that delta is much smaller than e, which is the case, right? E is very, very large, delta is small. So I can take a Taylor expansion here, right? So if I do the Taylor expansion, I get V to the n, H to the 3n, C 3n, and then square root of 2m times E 3n. By the way, you see that this is nothing but sigma. This is sigma of E times this other guy, But this other guy, if I now expand it, so how can I write it? Is exponential of 3n log of 1 minus this stuff. So which is log of 1 plus 3n over 2. Log of 1 plus delta over e minus 1. I further expand it. I never did this calculation with this example, so I'm doing it here. So I apologize if I'm a bit confused, or slow, but I think it makes a lot of sense. So this is going to be exponential of minus 3n over 2 times delta over e minus 1, right? And this is going to be equal to sigma of e times just a second, plus times roughly 3n over 2 delta over e plus other terms. And now you see explicitly what happens. When I take the log of this, okay, so let's do it here. When I take the log of sigma, the log of gamma, you see that what I wrote down here means that this is equal to the log of sigma plus the log of 3n delta over 2e. But this is a correction that is much, much smaller than log of sigma itself. Log of sigma is extensive. It's actually a constant because e is extensive and n scales like n. And therefore this can be neglected. All right? In the thermodynamic limit, this is equal to this. You see it now? For this particular example.
Yes.
Great. All right, so we will go on with this exercise next time, but at least you see now that these various definitions that I gave before make a lot of sense in this particular case. So you can use, in order to compute the entropy, sigma, gamma, or omega, and exchange them freely, simply because they have essentially the same scaling with the number of particles in the thermodynamic limit. So practically you can forget about the differences. And now, okay, next time I will start from this formula and I will show you that now if we use the entropy that we just found, I mean, we found sigma, we found also the entropy, and a few identities, we will be able to rederive the equation of state of the ideal gas starting from statistical mechanics, which is going to be our first success. Okay, so this is going to be the lecture. Are there other questions?
Yeah, Professor, just a quick one.
Yes.
Yeah, so in the various definitions of entropy, we see that we can also take it to be ln of sigma, but then we know
Yes.
that that constant, because okay, it's clear, but I'm still thinking of how that constant would sort of make a little bit of difference in the entropy itself.
Look,
The CN,
of course the definitions are,
C3N.
which C to the N? The C3N?
Yeah.
No, the C3N is always there. You see, what I've shown you here is that gamma look at the derivation. Gamma is equal to sigma times something else. But the C3n enters both in gamma and in sigma in the same way. See? Look at this formula. So the difference is this, actually. This factor here.
Yes.
But this factor is totally irrelevant for the entropy. I mean, it's much, much smaller than sigma itself. So when you take the log, it's just an additive constant that you can forget for all purposes. Okay?
Yes, sir.
Good. Other questions? Okay, so if not, let me show you my face. You can see it. Stop sharing. Okay, so thanks a lot for everything and for the questions. And we will be in touch on Friday, same time on this channel. Okay.
Oh, I didn't
Thank you,
realize.
Prof. Yeah.
Thank you.
Yes.
Thank you.
Thank you, Professor.
Bye-bye.
I didn't
Bye-bye.
realize it's
See
12:30.
you on Friday.
Thank you.
12:35. 12:35.